Thank you for your kind introduction. My name is Wiktoria Reddig, and the paper I'm about to present to you was done as a part of my engineering thesis and was done in a collaboration with Lukasiewicz Institute of Microelectronics and Photonics and Polish National Center for Nuclear Research. In our research, we are aiming at finding magnetic field detectors that are capable of working in tokamaks. Tokamak is a device that generates power using nuclear fusion, using powerful magnetic field that confines hot plasma in which the fusion occurs in the shape of a torus. These thermonuclear reactors are whole grail of carbon-free sources of power. However, they pose a very harsh environment for the electronics. It has to withstand very high neutron radiation of 10 to the 22 neutrons per centimeter squared, and high temperature of about 350 degrees Celsius. So now we can only simulate the conditions that are present in the thermonuclear reactors using research fission reactors. Here you can see the Marta research reactor in Polish National Center for Nuclear Research. On the right, there is a top view of the reactor pool, and on the left, there is a cross-section of the core. We did preliminary research using the reactor, and we did find some changes in electrical parameters of our sensors. However, during the irradiation process, a lot of energy is dissipated in form of heat. So what I will present to you today is actually the electrical measurements of the sensors that were not irradiated. However, they experienced the same temperature conditions as the irradiated ones, because our goal here is to show whether the changes that we've seen were caused by the neutron radiation or high temperature. So we are researching two types of platforms. One is graphene-based. Here you can see the graphene marked with the black cross. And the other one is indium antimonide-based in form of a thin film. We've chosen those materials based on their general temperature stability and very high sensitivity in comparison to other materials used generally for this purpose. When comparing the results on the right, mind the logarithmic scale. And sensitivity basically tells us how stable the whole voltage is, so it is a very important technological parameter. Now I will tell you more about our materials. So the first platform is epitaxially grown graphene on silicon carbide. Graphene is a 2D material. However, for practical use, it must be a part of a 3D system. This means that it will lose some of its freestanding properties, right? For this reason, we intercalated graphene with hydrogen so that it will not be connected with the substrate and gain quasi-freestanding qualities. It is also passivated with 2O3 to prevent absorption of any impurities, and is also equipped with golden electrodes and the titanium buffer layer for better contact resistance. The other platform is indium antimonide that is Sn-doped for better temperature stability. It is grown in gallium arsenide substrate and also have golden electrodes here with chromium batholea. Here we have a thin film as a part of a 3D system. During the next presentation, this material will be, there will be more about this material, so I won't elaborate on that now. What we are actually measuring is the Hall effect. I hope you know that the Hall effect is this phenomenon that occurs in the materials that conduct current while there is applied an external magnetic field that is parallel to the direction of the current. Then the charged particles experience the Lorentz force that pushes them to the sides, creating the lateral potential difference called the Hall voltage, which we can measure. And okay. There was the picture with the holder that holds the holds the sample, and so we can make the 4-point measurement of the samples and measure the Hall voltage and sheet resistance, from which we can calculate the carrier mobility and carrier density. The holder that you cannot see here is a ceramic one, which allows us for precise temperature changes and to modify the temperature of the sensor. So to see if the changes that we measured were caused by radiation or high temperature, we devised 2 procedures. One, pictured above, long-term constant with constant temperature, was mimicking the conditions that were present in nuclear fusion reactor. The samples there experienced 100 hours of annealing in about 200 degrees Celsius. This on this picture is only a simplified version. We actually did 10 cycles lasting 10 hours each in 200 degrees Celsius. And the other procedure, the variable temperature one, it actually mimics the procedure that we applied to our irradiated sensors to like see how they changes after irradiation with temperature. So it's just a direct replica of those conditions. Each point represents here a temperature and time of measurement of a single Hall measurement. And with the black dots, you can see the measurements in room temperature, which will tell us a lot about the changes, those permanent changes in between cycles. Here we have gathered results of every measured sample, every sensor, before and after every procedure. And in general, the changes are really minimal. In general, none of these changes exceed 5%. In terms of the first procedure, the graphene was this like 5% change, it experienced this 5% change. The indium antimonide one experienced like 1% change, so it is really good stability. Now let's dive into the second procedure results. Here you can see the carrier mobility and density results. The points indicate the room temperature measurements. With red circles, we mark the indium antimonide sensors, and with the blue squares, there is graphene. As you can visually see, during this whole process, they were all very stable, and the procedure did not really affect and did not any permanent damage to the sensors. But let's see what happens in between the cycle using the example of the 5th cycle. Here you have sheet resistance and hole voltage, so the pure things that we measured of both of the samples. The graphene one, of course, they do change. However, the graphene changes more uniformly. The changes are maintained throughout the whole cycle, and the indium antimonide experiences a sudden change around 200 degrees Celsius, which is connected to the fact that this material has a melting point at 525 degrees Celsius. So the closer we get to this temperature, the more sudden changes we will expect. Nevertheless, to judge the quantitative impact of the procedure, we need to introduce thermal stability coefficients. We'll use alpha and beta as that will tell us the percentage change of hole voltage and sheet resistance over a given period of given range of temperature. And so when we take an average thermal stability coefficients for both of the platforms and for both of those parameters, you can see that none of them exceeds really 1/10% per degree Celsius. Even further, when we look at the indium antimonide results for only up to 200 degrees Celsius, it can even be as low as 0.003% per degree Celsius. And that will bring me to the conclusions that the long-term annealing and the variable temperature procedures, they do not really affect our sensors. The thermal stability coefficients prove better stability of the graphene up to 350 degrees Celsius. However, if we just take this range up to 200 degrees Celsius, it is the indium antimonide that has better temperature stability. Overall, however, we can see that after this irradiation, the changes that we measured were not caused by high temperature, but the radiation. So this is our team, and thank you for your attention.